All listeners, I am Pawan Kumar, Assistant Professor, School of Sciences. Today we will discuss Introduction to Limits of Real Valued Functions 1. So we will discuss in this presentation defining real valued functions, what is limit, then graphical approach of a limit, then numerical approach of a limit, then intuitive definition of limit, and then evaluating limits algebraically. So let us come to first a real valued function. A function f from S to R, where S is a subset of R, is called a real valued function. For example, f from R to R defined by fx equals to 2x square plus 1. So this is a real valued function. Here the function has the set of all real numbers and its range is the interval 1 to infinity. There are many other examples also. Fx equals to sin x. This is a real valued function. Here x belongs to R. Its domain is the set of real numbers R and its range is the interval, the closed interval -1 to 1. So for example, another function fx equals to 1 upon x square. Here the domain is set of all real numbers excluding 0, because at 0 this function is not defined. If you put x equals to 0, you will get 1 upon infinity or 1.0, sorry, and that becomes infinity. So function is not defined at 0. So its domain is minus infinity to its domain is r minus 0 and its range is R. What is a limit? You may think that reaching towards something is a limit. So if we consider the example 1, suppose a train is running from New Delhi to Chennai. Its arrival time at Chennai station is 2 am. Now, as the time reaches to 2 am, the train also reaches towards the station. That is, the distance between the train and the station decreases to 0. So if we take dt equals to the distance between the train and the station, we express it as limit t tends to 2 dt equals to 0. Consider another example. A ball is released from a state of rest and falls to the earth. Distance travelled by the ball after t seconds is ft equals to 16 t square ft. Ft means here foot. Assuming that s0 equals to 0, how do we find the instantaneous velocity of the ball at time t equals to 1? So to find the instantaneous velocity, let us find first average velocity at the time interval 0.6 to 1. So the change in the position is s delta s equals to s1 minus s.6, that is 10.24, and the change in time is delta t equals to 1 minus 0.6, that is equal to 0.4. Now Using the formula of average velocity, we calculate average velocity equals to 25.6 feet per second. So this is the average velocity in the time interval 0.6 to 1. Now suppose if we shrink the size of the interval, then the corresponding changes in STR as according to table 1. So the time interval, when time interval is 0.6 to 1, average velocity is 25.6. When the time interval becomes 0.7 to 1, the average velocity becomes 27.20. When the time interval is 0.8 to 1, average velocity becomes 28.20. Similarly, when the time interval goes on decreasing in size, and finally when it is 0.9999 to 1, the average velocity is 31.9984. So you can observe something from this table. There is clear trend that is emerging from this table. The trend is when the time interval is reducing, the average velocity is reaching towards 32. So as the interval size is reducing, that is the time is approaching to 1, the values of ST are approaching towards 32. In mathematics language, we can say then 32 is the limit of ST as t approaches to 1, or in symbolic way we write limit t tends to 1 ST equals to 32, or another way is ST approaches to 32 as t approaches to 1. You can note one thing, that size of the interval is shrinking from left of the point 1. Suppose if you take the intervals which are in the right of 1, then you can also see that their size gradually reduces to 0 and ST approaches to 32. Now let us take some real valued functions. The function fx equals to x square minus 4 upon x minus 2, x is not equal to 2, gx equals to x square minus 2 when x is less than 4, 3x plus 1 when x is greater than 4, and hx equals to x plus 2 when x is less than minus 1, and x cube minus 7 when x is greater than minus 1. So in these three functions we have seen that f2 is not defined, g4 is also not given, h minus 1 is also not given. So we cannot find their values, but we can certainly try to reach their values. Let's consider the function f. f2 is not possible to determine, but we can find values of f at points near 2, and gradually we can reach towards f2. This can be shown graphically as follows. Consider the graph. This graph is a straight line, and at the point 2 there is a hole. So it means that the function is not defined at 2. Now we see the table. When x is 1.5, fx is 3.5. When x becomes 1.9, fx becomes 3.9. When x becomes 1.99, fx becomes 3.99. When x is 1.999, fx is 3.999. So we are seeing that when x is reaching towards 2 from the right hand side, fx is reaching towards the number 4. Similarly, when x reaches towards 2 from the left hand side, that is when it takes the values 2.01, 2.1, 2.5, then the function tends to the number 4. So we say that fx has the limit 4 at x equals to 2. Now we will define limit intuitively. So to say limit x tends to c, fx equals to L but not equal to c, then fx is very close to L, or in other words, the difference between fx and L can be made as small as possible by taking x sufficiently close to c but not equal to c. Why we do not take x equal to c? Because we have already seen that at x equal to c, if a function is not defined, then we cannot find the value of f at c. So we try to reach towards c. Consider some examples. Find the following limit. Example 1. Limit x tends to 3, 3x minus 7. And example 2. Limit x tends to 9, 3 upon x plus 2. So we are considering 1. So the table is given here. There are two tables. In the left hand side, the table shows that x approaches to 3 from the left hand side, and in the table given in right side shows that x approaches to 3 from right. So let us now consider table in the left hand side. So here when x is 2.5, fx is 0.5. When x reaches to 2.7, fx reaches to 1.1. When x reaches to 2.9, fx reaches to 1.7. When x reaches to 2.99, fx reaches to 1.97. Similarly, when x is 2.99999, fx is 1.999997. That shows that when x is very close to 3, fx becomes very close to the number 2. Now let us come to the table given in right hand side. When x is 3.5, fx is also 3.5. When x reaches to 3.2, fx reaches to 2.6. When x becomes 3.1, fx becomes 2.3, and finally when x is very close to 3, that is when x is 3.00001, then fx becomes 2.00003. So this shows that when x is reaching towards 3 from the right hand side, fx is reaching towards 2. So now combining both these tables, we see that when x reaches towards 3, whether from left hand side or from right hand side, fx reaches to the unique number 2. So 2 is the limit of fx at the point x equal to 3. That is given here. So we write it as limit x tends to 3, 3x minus 7 equal to 2. Similarly, we can do the other example. Now let us take the function fx equals to x sin 1 upon x if x is not equal to 0, and it is 1 when x equal to 0. So clearly f0 is 1. Now let us have a look on the graph. See, when x is reaching to 0, f is also reaching to 0. You can see either from left hand side or from the right hand side. That is, from both the sides, when x is reaching to 0, f is reaching to the unique number 0. So f has limit 0 as x tends to 0. Now there may be some examples where the limit does not exist, like the limit does not exist at jumps. For example, you consider this graph of some function. Here x is tending to 0 from left hand side, then function is tending towards 0, and when x is tending towards 0 from the right hand side, f is tending towards some positive number. So there is a jump. When x passes through 0, the function has a jump. So that means when x tends to 0, function does not approach to a unique number. That's why the limit does not exist. Now let's consider some more functions where the limits does not exist. For example, limit x tends to 0, sine 1 upon x, limit x tends to 8, x minus 8 upon mod x minus 8, and limit x tends to 0, 1 upon x. So let us see the graphs of these functions. And so this is the graph of the function fx equals to sine 1 upon x. Here we see that when x is reaching to 0 from left as well as from right, when x is very close to 0, the function oscillates infinitely many times between -1 and 1. So we cannot say that function is reaching towards some unique number. So that's why the function does not have limit as x tends to 0. Okay. Next, consider the function fx equals to x minus 8 upon mod x minus 8. Here when x tends to 8 from left, the function is -1, and when x tends to 8 from right, the function value is 1. So that is, when x crosses 8, function has a jump. So function does not have a unique value when x reaches towards 8, and that means fx has no limit at the point 8. Now consider the function fx equals to 1 upon x. As you can see the graph, when x tends to 0 from the left hand side, the function fx tends to -infinity, and when x tends to 0 from the right hand side, fx tends to +infinity. So in this case also, fx has a jump when x crosses 0. So fx has no limit at the point x equals to 0. So in the examples above, it can be seen that the limit at given points does not exist, as we have explained, because the functions have jumps at the given points. Now note that L is the limit of fx at c if fx is reaching to the unique number L whenever x is reaching to c from both the sides of c. More clearly, if fx tends to L1 when x tends to c from left side, and fx tends to L2 when x tends to c from right side, and if L1 is not equal to L2, then the limit does not exist. That means limit will exist only if L1 equal to L2. So we have seen that when x reaches to c from left hand side and from right hand side, if function has different limits, when x tends to c from right hand side and from left hand side, then we cannot determine the limit, or we say the limit does not exist. But we can now talk about one-sided limits. So we can, when x is reaching towards c from the left hand side, and if f is reaching to some number L, then we say that L is the left hand limit of f at c. It means that the difference between fx and L is reaching towards 0 when x is reaching towards c from the left side. Similarly, we can define the right hand limit. So we say limit x tends to c plus fx equals to m if difference between fx and m tends to 0 when x tends to c from the right hand side. Now consider this graph. Can you observe what are the left hand and right hand limits? If you look at the graph, we can see that when x is reaching to 0 from the left side of 0, fx is reaching to 0, and when x is reaching to 0 from the right side, in this case also fx is reaching to 0. So f is reaching to the unique number 0 when x is reaching to 0 from both the sides. So f has the limit 0 as x tends to 0. Now consider some examples here. In these examples we will find left hand limit and right hand limit. So the function here given is fx equals to minus x plus 1 if x is less than 1. It is x minus 1 if x lies strictly between 1 and 2, and it is 5 minus x square if x is greater than or equal to 2. Let us find the left hand limit, right hand limit, and the limit of function f at the point 1 graphically. The graph for the function is given here. It is a straight line from 0 to 1, and at the point 1 it is not defined, and then in the interval 1 to 2 it is again a straight line, and from 2 to onwards this is given as a curve. Now when x tends to 1 from left hand side, f is reaching to 1, and when x tends to 1 from the right hand side, f is also reaching to 1. So f is reaching to the unique number 1 when x is reaching towards 1 from both the sides. So the limit, the left hand limit is 1 as well as the right hand limit is 1, and both the limits are equal. So the limit of the function exists and is equal to 1. Similarly, at the point 2 we can find the limit. Again, if you see the function, we can see that when x equals to 2, the function value is 5 minus 4, that is 1. So when x is reaching to 2 from the left hand side, the function reaches to 1, and when x is reaching to 2 from the right hand side, function also reaches to 1. So f reaches to a unique value 1 when x reaches to 2. So the limit of f at x equal to 2 is 1. Okay, as we have explained this, now you can see something that in these examples we have used the graphical method. That means we have found the limits of the functions using their graphs, but many times we are not able to draw the graph of the function. In that case, this method cannot be helpful to evaluate limits. Then we come to the algebraic method. In this method, we try to simplify the functions in its lowest, simplest form by factoring or rationalizing or expanding it. and finally substituting the limit in the function. Just consider these examples. Limit x tends to 2, x square minus x minus 2 upon x square minus 5x plus 6. Second, limit x tends to 2, under root x plus 7 minus under root 7 upon x. Third, limit x tends to 16, square root x minus 4 upon x minus 16. Fourth, limit x tends to 0, square root 1 plus x minus square root 1 minus x upon x. So let us find the limit of the function given in example 1. Here limit x tends to 2, x square minus x minus 2 upon x square minus 5x plus 6. So we can see that x square minus x minus 2 has a factor x plus 1 and x minus 2, and the denominator x square minus 5x plus 6 has a factor x minus 3 x minus 2. So this limit can be written as limit x tends to 2, x plus 1 into x minus 2 upon x minus 3 upon x minus 2. So x minus 2 cancels each other from numerator and denominator, and it remains limit x tends to 2, x plus 1 upon x minus 3. Now it is in the simplest and lowest form. Now we can substitute x equals to 2 to evaluate the limit. So this becomes 2 plus 1 upon 2 minus 3, that is minus 3. So its limit is minus 3. Now consider the second example. Here limit x tends to 0, square root x plus 7 minus square root 7 upon x equal to, so here we rationalize this so that the numerator can be simplified, because if you just substitute x equals to 0 in the numerator and denominator, we will get 0 upon 0, which is an indeterminate form, so its value cannot be determined. So we rationalize this and we get limit x tends to 0, x upon x under root x plus 7 plus under root 7, x cancels x, so it is equal to limit x tends to 0, 1 upon square root x plus 7 plus square root 7, and now we can substitute x equal to 0, so we get 1 upon 2 under root 7, which is the required limit. Now consider the example 3. Here the function is square root x minus 4 upon x minus 16 equals to limit x tends to 16 and square root x minus 4 upon the square root x minus 4 into the square root x plus 4. Here x minus 16 has the factors the square root x minus 4 and the square root x plus 4. So the square root x minus 4 which cancels from numerator and denominator, and it remains only limit x tends to 16, 1 upon the square root x plus 4. Now this is in the simplest form. We can substitute x equal to 16 and we get 1 upon 8, which is the required limit. Next we take the example 4th. Let us solve this as it is giving limit x tends to 0, square root 1 plus x minus square root 1 minus x upon x. If we substitute x equals to 0, here we get 1 minus 1 upon 0, that is 0 by 0. The value of 0 by 0 cannot be determined, so we try to reduce this expression into its simplest form. For this, we have to rationalize this. So now this is equal to limit x tends to 0 square root 1 plus x minus square root 1 minus x upon x, and we multiply here with square root 1 plus x minus square root 1 minus x and divide by the same we will multiply here with square root x plus 1 plus square root 1 minus x and divide by 1 plus x plus square root 1 minus x. So see the numerator, this is in the form a minus b into a plus b. So we can apply that formula and we get here limit x tends to 0 1 plus x minus 1 minus x upon x square root 1 plus x plus 1 minus x. So which finally reduces to limit x tends to 0 2x upon x 1 plus x plus square root 1 minus x. And now x cancels this x, and now we can substitute x equals to 0 here. So when we substitute x equal to 0, we get 2 upon 1 plus 1, that is 1. So the limit of this function is 1 when x tends to 0. So in this session we have defined real valued function. We have introduced the limit, taking real life situations, and discussed various examples of intuitive limits graphically and numerically, and we have computed limits using algebraic method for various real valued functions. So dear listeners, I hope you have got what is a limit. If you have any doubts, you can ask. Thank you.